Let's explore rigid body dynamics by recreating this simulation. So the reason I chose this is there are two static objects, a tube which has a hollow interior, and then a ground which is also curved. Both of these will allow us to encounter some gotchas that are pretty common when you're creating your first simulation. So with that in mind, let's get started. For this simulation, we're going to have three objects: the ball, the tube, and the ground. So we're going to create a geometry network and make two more copies. Let's select these, and I'll use the layout features to align them vertically and distribute them vertically. There we go. The ball will be moving around, so that's going to be a dynamic object in our simulation. So I'm going to call it dynamic ball. The ground will be static, so I'm going to call that static ground. And finally, the tube is also going to be static. It doesn't move around, but it does participate in bounces and stuff. Not static ground, sorry. It is static tube. And instead of dynamic ball, let's call it RBD ball, because RBD stands for rigid body dynamics, and that's the type of object we'll have to convert this to create the simulation. So let's first create the tube. We're going to come in, create a tube, zoom in on it, space G, and we select this little doohickey here. We're going to make it about, how about 50 rows and 50 columns. That way we have a finer mesh so that when we bend it, like we saw in the simulation, the bend will be a little more curvy than, abrupt and polygonal. Let's make the height of this 10 meters and zoom out. So there we have a tube. I'm not putting end caps on it. We want the ball to go through the tube. And as good practice, I'm going to put a null output next to the ground. Actually, I'm not done with the tube. We need to bend it. So I'm going to come in here and add a bend node. There we go. And you have to specify what the capture region is. So what part of the geometry will bend. And so we want to bend the bottom half. So that's pointing in the negative y direction. So the capture direction is going to be 0, -1, 0. The capture length, since this is a 10-meter long tube, the capture length is going to be 5 meters because we want to get the bottom half. So capture length will be 5. Now if we use this handle here, we can rotate it as much or as little as we want. I'm going to rotate it about -60 degrees. I can just type that up here. There we go. So we now have the tube, we bent it, and we have an output. Now let's come up here and create the ground. The ground is going to be a grid, and like before, we want a fine mesh. I'm going to do 100 by 100. Notice that it's cutting off the plane. We'll fix that in a second. So let's bend this. So we'll just add another bend node. So we're going to bend in this direction, and we want to capture half of it like we did with the tube. So this direction is the -x direction. So the capture direction is going to be -1, 0, 0. And the capture length, the grid is 100 meters by 100 meters. So let's make it 50. Sorry, it's not 100 meters by 100 meters. If you select the grid, you can see it's 10 meters by 10 meters. I was confusing the number of rows and columns with that. So it's actually 5 meters for a capture length, not 50. Okay, now let's just bend this up a bit. How about let's go up to 40 degrees. Okay, there we have a nice looking curved ground, a tube that's bent. What we now want to do is just take the curved ground, move it down, and also then rotate it. So let's add a transform real quick. And I'd like to first move, then rotate, and in the transfer node you specify what the order of operations is, because a transform can scale, transform, or translate and rotate, and it can do all those things. You just have to let it know what order you want it to do, and then also what's the order of the X, Y, and Z operators that you want to do. And so it gives you all possible combinations. We just want to translate, then rotate. And so we're going to translate it down. And let's select this here. And let's just go down a little bit more. So -5, I believe, is what would take us to the bottom of the tube. Let's just go ahead and go down to -6. Okay, and next is we're going to move it to the -x direction a little bit. So we're going to translate it. How about -2? Now we're going to rotate. So we translated first, now we're going to rotate. We're going to rotate it around the y-axis, just so when the ball comes out, it'll kind of curve off in one direction and look kind of neat. So I'm going to take and rotate it. How about if we go -20 degrees, you can see when the ball comes out of the tube, it's going to go off in this direction and then fly off. So we may not want to do -20. Let's do -10. That'll give it just a little bit of movement in one direction. So there we have our two static objects. And let's do the null output again. Control A, select everything, and do the alignment and distribution. So align vertically, distribute vertically, nice and tidy. Okay, now it's time to create the ball and do the simulations. We're going to create a sphere, and for the sphere, we are going to not use a primitive. We're going to use a polygon mesh, or how about, polygon mesh with how about 25 rows and 25 columns. That'll make it fairly round. Next is we'd like the sphere to start just above the tube, so let's move it upwards in the y direction. Let's see if we move it up 5. That puts it at the beginning, so let's go up 6, so it's definitely starting above the tube. Now right now, it's the same diameter as the tube. We'd like it to be a little bit smaller, so let's just decrease the radius down to 0.3. And then also, if we look down, you can see that the ball is going to go straight down in the middle. Why don't we just move it a little bit in this direction? There. So while it will still go into the tube, let's make this 0.15, it will hit the edge of the tube a little bit earlier than it would otherwise. It just will make for a more interesting simulation. So let's take the sphere, null output. We now have our three objects and we're ready to do a simulation. Simulations are done inside a DOP network. DOP stands for Dynamic Operators, so let's create a DOP network. And when we come in here, you'll notice that, these are kind of shadowed out. That's because in this network so far, there's no geometry. We have to bring in the objects that we want Houdini to use when it's running this simulation. So we have two static objects, tube and ground, and one rigid body dynamic, one object that's actually going to be moving around, bouncing and sliding, and that's the ball. So for static objects, you import a static object. This tells Houdini that this object should not move. It's just going to, it will participate, like things can bounce off it, but it's not going to move at all. I'm going to select the soft path, select static ground, accept it. I'm going to call this DOP ground, just so we can, rather than static ground, because I don't want to reuse the name. This way we'll be able to tell the difference as we hop around. We're going to import another static object, and we're going to bring in the tube, the static tube, and I'm going to rename this DOP tube. Now for these, let's just select both of them, come down, merge, and wire the merge up to the output. Okay, let's move this to the beginning. I've noticed that until you move the playhead, sometimes the view doesn't refresh. So we brought in these two objects, merged them, wired it to the output, and they didn't appear active until I just kind of wiggled the playhead. I'm sure there's a setting somewhere, or that just might be a quirk of Houdini, I'm not sure. Now, if we hit play, nothing happens. There's no forces, there's no solver, and there's no ball yet. So let's bring in the ball. The ball is not a static object. We'd like it to move it around. And so it is an RBD object. And they have the little rubber ducky as the icon for that. Now we can bring this over into the merge node as well. And once again, notice how the ball is still grayed out, but if I just move it a little bit, especially to the beginning, there's the ball. Oh, my apologies, I forgot to set the soft path. So we're going to come over here, RBD ball. There we go. So we have the ball, the tube, the ground, and if you hit play, nothing happens. Now, one thing that separates dynamic networks from geometry networks is that the order is not as important. It is to some extent, but it's not vitally important. The way these networks are built is more like you're telling what ingredients you want Houdini to use when it does the calculations and creates the animation for us. The key to doing that is a solver. Hit tab, come down to solvers, and these are all the basically algorithms or brains of the outfit that will do the calculations necessary from frame to frame and even between frames to make sure that everything that's happening on the screen is adhering to the rules that you've set. Like if you want the gravity to be equal to what the gravity is on Mars, it'll make sure that it uses that. If there's a wind or there can be a tornado going by, it needs to be able to update everything, all the velocities, accelerations, positions of all the geometries to be able to make that convincing. Now, they have things for fire, for smoke, vellum, which is a very flexible one, but we're just going to work simply with rigid bodies. Now, there is the bullet solver, which is one way to do it. There's the RBD solver, and there's the rigid body solver. The rigid body solver is effectively the RBD solver and the bullet solver combined. So we're going to use that. Now, where do we put this? So we want to put this in a place so that everything above it, if you will, is marked as saying we want it to be under the influence of this solver, the solving algorithm. Now, we could put it here, and we won't get in trouble because we've already told Houdini these two are static, meaning their positions aren't going to change. So we could put it there if we wanted. But we could also take and snip this and move it here so that the RBD object, the ball, is now needs to be controlled by the rigid body solver. I'm just going to call this operator solver. And there we go. Now, if we hit play, what will happen? Nothing, because right now there's no forces. There's no wind, there's no gravity. We actually have to add those. So where do we add gravity? We can add gravity. We want gravity to affect our ball. So let me call that dot ball. Forgot to rename that. We want the solver to use gravity. So we could just kind of put it in this chain here. We could even put it here if we want. So there's a couple places we could put it, but let's just put it here. By default, gravity has a downward force of negative 9.8 meters per second squared. That's the gravity on Earth. So it defaults to Earth, but you can come up here and easily change this to whichever planet you'd like to work with, or just set it to be 0 if you're in outer space, but if you're in outer space, you wouldn't use the gravity node. Now let's hit play and see what happens. Okay, that's a little kind of anticlimactic. It just fell down to the tube and bounced off it, even though the tube is hollow. Also, we can still see the ghost of the geometry node. So I'm going to take the 3 geometry objects and just hide them. Let's come back into our simulation and understand why it's not going through. And this is a common gotcha when you're first starting. It's like, and it's kind of really disappointing. It's like, okay, you went through all the work, you created this dynamic network by hand, you're not using the shelf tools, and this happens. So what is going on? Let's select the static object, the tube, and look at the parameters here. We have physical and collisions. It's the collision properties that we're really interested in. And notice you have RBD solver and bullet data. Remember earlier I said under solvers, this rigid body solver is a combination of RBD solver and bullet solver. So which one are we using? If you select the solver, you can see we're using bullet. So if we come back now to the tube and come to collisions, you have to specify how you want collisions to be handled. Out of curiosity, if we hit the solver and switch it to RBD solver, let's see what happens. Does that work any differently? A little. I mean, it fell down and is just stopping in midair. In both cases, there is an additional detail we need to pay attention to. Let's click the solver and go back to bullet. Now let's go to the tube, come over to collisions and bullet data. Here is the trick, show guide geometry. This shows you how, when doing the calculations, Houdini views that tube. It doesn't view it as a tube, it views it as a solid convex object. A reminder, a convex shape is any shape where any 2 points can be connected by a straight line without leaving that shape. Another way to think about that is if you were to shrink wrap this, like just put a bunch of plastic around this tube and suck out the air until it's really taut, this is the shape you would get. Assuming we don't we want fairly rigid plastic. We don't want it to kind of bend in and be like saran wrap. So why did it do that? And also other geometry representations, there's other ways you can tell Houdini to treat this object when it's doing the simulation. You can say box. Here's the smallest box that contains the tube. Hit play and the ball just rolls off the box. Or you could come over here and say cylinder. If we hit play, it hits the top of the cylinder and rolls off. So none of these are really what we're after. You could even do a sphere, by the way, which is a little wacky. Hit play and it's just going to roll off the sphere into oblivion. What we want is to select concave. When you select concave, it will handle these gaps and hollows and hollowed out aspects of the shape. It will treat it essentially as you made it. The reason it doesn't do that by default is concave shapes are more expensive computationally. So working with convex objects is much more efficient to do. So if you're doing a rigid body simulation where you have a wall that's been fractured and a ball is just going to crash through it, you can treat all these little objects and the shards and everything as convex objects and it'll still look great. But if you're going to do something more complicated where you have like hollow tubes and balls going through them, you need to select the geometry representation to be concave. So let's turn this off. Now let's run and see what happens. Okay, the ball falls through the tube and comes out. Let's rewind and see that again. If I select the DOP ground and say show geometry, that is how Houdini is treating the ground in the simulation. So if we rewind, we need to be careful. Like if I had turned this off and we looked at it from the side, you would have noticed it. So let's rewind to the beginning, play, and notice the ball is like bouncing off air. And so from this way, it wasn't quite clear that that's what was happening. So like from this angle, I almost could believe that it was bouncing on the ground. But if you look at it from the side, play it again, you can see that it is bouncing on what seems to be air. And the reason for that is the ground, if you show the guide geometry, this is how it's being treated. That's not how it's being shown. It shows the true geometry, but when computing the motion and reflections and bounces, this is the shape that it's using. So we want to switch this also to concave. Notice the color switch from blue to orange. Clear the cache. That's what that means. Blue means you have some cached data. So now let's play this again. Comes down and it goes off. Alrighty. How can we prevent it from going off? We'll get to that in a second. So here we go. Here we built the simulation by hand. We have two static objects. We brought in the ball that'll move around, and it needed two things. It needed a solver and it needed a force, in this case, to just make it fall. Let's come back up. Notice that the geometry is not visible, the .NET is. If we hide the .NET, nothing's visible. Let's select the geometries and toggle the display flag. Now, if we hit play, nothing happens. That's because the geometry has no motion in it. If you come in, this is just a basic sphere. The ground is just a grid that's been bent, and the tube is just a tube that's been bent. There's no operator in there moving anything around. The only network that has that is the .NET. So let's hide the geometries, the static geometries, and then show the .NET. Run it. I'm going to rename .NET simulation. And let's fix it, the ball just bouncing off. That's not terribly satisfying. So we're going to come to the ground, come to the grid, and we're going to make it, how about 20 meters by 20 meters. There we go. We have a much bigger ground for the ball to collide with and roll around on. Let's go to the beginning and hit play and see what happens. There we go. And it flies off into infinity and beyond. So let's go to the beginning. There we go. And to speed this up, you can actually make this go a little faster just for demo purposes. If you click the global animation properties, this little window here, real-time playback is selected, and you could say, let's play it back twice as fast so we don't get impatient. Play. There we go. Twice as fast, and we can see the ball rolls up, down, and all around. That is one way to create a simulation in Houdini, a rigid body dynamic simulation. I want to show you another way. So let's hide the simulation, select our geometries and show those. What we're going to do now is the ground and the tube are static. They don't do anything, so we don't have to do anything with them. But we're going to come into the RBD ball. What we're going to do is say, here's the geometry. We're going to add just one node that will bring all the calculations from the simulation in and apply that to the ball. And that is called the DOP import. The DOP import, you need to first select what is the network that's doing the calculation. That's the simulation. Select it. Little green clock watch, stopwatch here to let you know that parameters are changing as a result of that. Object mask. Which object from this simulation do you want to use? We are going to use the ball. And then lastly, use single object. So we're going to come up here and hit play. But there we go. So what we have here now is the simulation, although it's not displayed, it's still doing the calculations. In the tube network, nothing's happening, no change. The ground network, we've made no changes. All we did was go to the ball network and add a single node, and that was to, I'll call that, how about sim motion? Is we said using this DOP network, take this object from the simulation and then use a single object and then transform the geometry that's coming in. So that's another way to create a simulation and have the visible flags on the geometries turned on as opposed to the network. Now, why even have that alternative way to do it? You know, doing everything in the simulation seemed to work just fine. If we select that, hide the geometries, hit play, it works just fine. One reason I found is, especially using Solaris now as the styling, lighting, rendering pipeline, is by having these separate objects as separate level nodes, then when I go into Solaris, I'm able to just easily bring those in. And when I try to bring in a DOP network and the objects in them, I was running into some problems. But also, it's important to understand that oftentimes there's more than one way to do something. Let me show you another way. So I'm going to delete the DOP network, come into the ball and delete this DOP import. So we're back where we started. We have three basic geometry objects, no simulation at work. We're now going to use the shelf tools and see what it does. So I have a simplified toolbar here for presentations. So we're going to come to collisions, and it has static objects. So the ground will be static. Let's select it and click static. That's great. One thing it did was it created a new network, a new DOP network called AutoDOP network. And as the name implies, this was created automatically. We didn't have to do anything. If we go into the AutoDOP network, you can see it created a static object from the ground, merged it with nothing, attached a static solver. We're not going to talk about that today. Merged it with nothing, applied gravity, and then you have the output. There's no solver attached because so far it's just static objects. Let's select the tube. Let's make it static as well. Come into the DOP network, L for layout. Now you can see it imported both the tube and the ground as static objects, merged them, attached a static solver, which in many cases is optional, merged it with nothing, gravity, output. Finally, we're going to take the RBD ball. We're going to come to rigid bodies and say this is our RBD hero object. Now if we come in here, L for layout, H to zoom it so that we can see everything. Here's the static side, here's the dynamic side. Static side is the same. Import them, merge them, and add a static solver. Here brings in an RBD object, merge node, adds the rigid body dynamic solver with the bullet engine selected, which is what we did. Merge them, add gravity, and then output. Now, if we come up here, and by the way, if you come into the geometries, you'll see this added two things. It added to the rigid body, the one that moves around, added a REST node and a DOP import. We only used a DOP import. Under the static ground, look what it did. Added a collision source, attribute create, over here a file cache, and a null node. Same with the tube. And so if we hit play, let's see what happens. Same thing happened that happened earlier, and that is because it's treating the static objects as convex hulls. That's the internal representation it's using to do the calculation. So we have to go into the DOP network, select each static object, go to collisions and say, under bullet data, make it concave. Same with the tube. Collisions, bullet data, concave. There we go. Up, rewind, and play. There we go. So that's a third way to do it, is you can use the shelf tools, but I prefer to not use the shelf tools until I understand exactly what they're going to do, because if I encounter any gotchas along the way, I'll understand why. So these are three different ways you can do a rigid body dynamic simulation. One is you can create the DOP network by hand, bring the objects in, attach the solver and gravity, and make sure that everything is set to concave, especially the curvy bits, and then let it go. The alternative is hide the network and go into the geometry, especially those networks of objects that are going to be moving and bouncing around, and basically import the transformation data from the simulation network and use that to control the movement of the objects. And then finally, which is kind of like a hybrid of what we did, is use the shelf tools, select which objects are RBD objects, which are static, and it will create this AutoDOP network for you. I hope you found this helpful, and have a good day.